Hello dear students, welcome to lesson 16 of structure of atom on the channel Learning Chemistry is Easy and Fun. In this lesson we are talking about orbitals, their types and shapes. Recalling what we did in lesson 15, orbitals. What are orbitals? It is nothing that you can say or that you can see in a concrete form. It is a three-dimensional region in space where the probability of finding the electron is maximum around the nucleus of the atom. This is according to the new model of the atom, the third model of the atom which we are doing, and that is called as the quantum mechanical model. Now the quantum mechanical model is based on the de Broglie concept of wave particle duality, that is the electron behaves like a wave as well as a particle, and it is also based on the Heisenberg's uncertainty principle, which says that you cannot exactly define or exactly say where the electron will be located. If you remember, I had given you an example of the teacher not being there in the class and the probability of finding the student can be anywhere but in the area of the class, right? So that is what we call as orbital, three-dimensional region in space. Unlike the Bohr's model, which said that the orbit is circular, right? So what we have over here is, now we are going to study the various types of orbitals. How we define them, how we got them, was done on the basis of the Schrödinger wave equation, the depths of which we are not dealing with at this point of time, right? So the various types of orbitals are the S, P, D and F. S stands for sharp, principal, diffuse and fundamental, depending on the types of the lines that we observe in the spectrum. At this level, and in fact at higher levels also, we usually limit ourselves, or we usually find ourselves focused on the S, P and the D orbitals, because the F orbitals assume a very complex shape, which is not required at the level of study that we are dealing with at present. Coming to the first set of orbitals called as the S orbitals. S is nothing but, S is sphere, right? So an S orbital is nothing but spherically symmetrical. Here I have represented a two-dimensional representation, but it is actually a three-dimensional structure. So that is why we are taking a ball as an example of a spherically symmetrical object. Now what happens is, here you can visualize the model of the atom on the basis of your school model. Like in your school, you have class 1, class 2, class 3 and so on and so forth. Now those classes further have subdivisions. So you have 1A, 1B, 1C, or in whatever format they are numbered. So each class or each year further has sections or subsections, what you may call. Now in a section, so let us suppose you are in 11B. Now in 11B, your area is confined within the four walls of that room. Now in the four walls of that room, you can be found anywhere when the teacher is not in the class. So that's your orbital area, right? Now what we have over here is the S orbital being spherically symmetrical means this is their boundary. So this is the area within which the electron can be found most of the time. Not all the time, because it can go a little out of that region, it can go a little closer to the nucleus. So it's quite random over here. Now what the electron is occupying is this orbital. What you are occupying in the entire setup of the school is this classroom. Now there are times when you go out of that classroom, when you have the snack break, when you go for your physical education class. So there are times when you are stepping out of this room, but the probability of finding you in the whole school is maximum within this zone. This is your orbital, right? Now, what happens now as the year group grows, so does the class size. So if in year 1 there are 10 students, in year 2 there are 20, in year 3 there are 30, and so on and so forth. So does the size of the S orbital. So here I am taking an simple case. I have this is 1s, that means the S orbital of the first shell. This is 2s. You see the size? What has differed here is only the size of the orbital. The shape remains the same. Let us say this is the S orbital of the third shell. So if you notice over here, we have the three S's. So we have 1s, 2s and 3s. Now all of them are spherically symmetrical. Spherically symmetrical around what? Around the x, y and the z axis. But their size has grown. Clear? Same thing we have represented over here. In the case of 1s, now this is my 1s orbital, that means the S orbital in the first shell. The 2s orbital is what is our second representation. Now if you notice over here, I have again represented these dots. Now by the way, what are these dots? These are, supposing I pictographically represent the position of the electron at any point of time, this is how I would get, right? Anywhere, it can be anywhere, but most of the time within this boundary. Similarly, when you are talking about 2s, anywhere around this, again we notice there's a slight gap, and anywhere, but it is most of the time within this boundary. The size of this sphere becomes bigger, one. Second we notice is that there is this region where the probability of finding the electron becomes least. It is, see this gap that you notice? This is what we call as the node. What is node? The region in space around the nucleus where the probability of finding the electron is 0. This has been graphically represented over here. So here, if you remember, we had mentioned psi square. Psi square is the probability density, the three-dimensional region in space where the probability is the highest of finding the electron. So if I have psi square on the y-axis, I have the distance of the electron from the nucleus on the x-axis. For the 1s orbital, what do we notice is that the probability of finding the electron closer to the nucleus is very, very high. As the distance from the nucleus increases, the probability of finding the electron becomes null. Coming to the representation of the probability density for a 2s orbital. Here again the probability of finding the electron closer to the nucleus is high as the distance from the nucleus increases. So as I advance on the x-axis, this graph is coming down. So what is happening is, as the distance from the nucleus is increasing, the probability of finding the electron reaches a stage where it is 0. See, this graph touches the 0 on the x-axis. And then again it rises and peaks over here. So the same thing is represented as a graph. So here the probability of finding the electron is high. There's 0 over here, what we call as the node, and again it rises, and then as we further increase the distance from the nucleus, the probability again starts reducing. You see, the probability again starts reducing and becomes 0. So what has happened over here is, only the size has increased. What has differed is, there is a region introduced over here where the probability of finding the electron becomes 0. So for S orbital, how many nodes will be present? So if it's 2, the number of nodes is 1. So we give a general representation for S orbitals. The number of nodes is equals to n minus 1. What is n? The number of the orbit for now, because we have not yet introduced the concept of quantum numbers, so I'm not talking about that at present. So for your simple understanding, the number of nodes is n minus 1. So whichever year group you are in, so if you are in class 11, number of nodes 11 minus 1, that is 10. If you are in class 6, number of nodes 6 minus 1, 5. Simple. That's how I will put it across. I know this is supposed to be principal quantum number. I'm not talking about it at present. I shall come to it in the next lesson. For now, let's go on to p orbitals. Now, this is what is a p orbital. Yeah, that's the simplest representation that I could find. What happens is, as the orbital value increases, as the distance from the nucleus also increases, the shape no longer remains spherical. There is a large zone where the probability of finding the electron becomes 0. And we represent the p orbitals in the form of a dumbbell. So we have over here p orbital, px, py, pz. What is this px, py, pz? It is nothing but a representation of the p orbitals in the 3 dimensions. Now here, take 3 pencils in your hand and stretch them mutually perpendicular to each other. What is happening over here is, the p orbitals, they are aligned along these 3 axes in the form of a dumbbell. So here, the probability of finding the electron above and below the nuclear axis is high here in this zone. Again I repeat, this is not the exact shape. These are only boundary surface diagrams that we have drawn, indicating 90% probability or 93% probability of finding the electron. The electron can move slightly out of it also. Now px means the dumbbell is aligned along the x-axis. So we have over here another representation. This are the 2 lobes of the px. Now if I am calling it as py, that means it's aligned along the y-axis. If I am calling it as pz, that means it's aligned along the z-axis. That's all. Px, py, pz representation can be anything. I can name this as y, this as z, and this as x. Don't get confused, because they are, all of them are mutually perpendicular to each other. Different texts prefer to name them differently. In many of the texts, you'll find this as y, this as z, this as x. They are all mutually perpendicular, represent the same thing. So if I am saying Px, that means the dumbbell is aligned along the x-axis. These three are mutually perpendicular. Very simple representation. This is how you do. Mutually perpendicular. If you remember, you've done it in the Fleming's rule also in physics. So this is how we represent mutually perpendicular. X, Y and Z. Same, if I'm saying Py, it's the same dumbbell but aligned along the y-axis. I'm saying Pz, same dumbbell but aligned along the z-axis. Now here the probability of finding the electron is 0 at this plane. If you notice my dumbbell here, it's squeezing in the middle, right? There's a gap in the two. Here the probability of finding the electron is 0. This plane along this nuclear axis, internuclear axis, the probability of finding the electron becomes 0, and that becomes the nodal plane. Coming to the d orbitals. Now d orbitals, if you notice, the shape again further becomes more and more complex, just like your studies. When you were in year 1, the studies were very simple. As you advanced and came to year 2, 3, and now that you are in 11, 12, whatever year you are in, the studies have become more and more complex, right? So this is your senior section now. That's the d orbital. Their shape becomes even more complex. Here, these are represented as dxy, dyz and dxz. So I have here dyz, dxz. Now, what do these mean? I have the x-axis, the y-axis. The lobes of the d orbital are aligned in between the x and the y-axis, and that becomes my dxy orbital. If on the other hand I consider the y and the z-axis, then this becomes my dyz. If I consider these as the x and the z-axis, this becomes my dxz. So don't get confused. It is very, very simple. I am not representing the third plane, the third axis, so as not to confuse you. In the books, you will definitely find the third axis drawn. Don't get confused at this point of time. Once your basics are clear, then you can draw all the three axes and show the shapes accordingly. Another shape, dx2 y2 or dx square y square, howsoever you may choose to call it. Now these are double dumbbells aligned along the x and the y axis. So this is one orbital. So in the case of S, you have 1. In the case of P, you have 3 p orbitals, px, py, pz. In the case of D, there are 5. 1, 2, 3, dxy, dyz and dxz. 4, dx2, y2. Fifth one is dz square. What is this dz square? It is like a dumbbell shape with a donut shaped ring around it. See, there's a ring around it in the form of a donut. Clear? This is my dz square. That's the fifth orbital. So as we said, S orbitals are only 1. If I am saying p orbitals, there are 3 p orbitals. If I am saying d orbitals, there are total 5 d orbitals. dxy, dyz, dxz, dx2y square, dz square. Now, exercise for you is as soon as you close the video, please try to draw these shapes yourself. Don't worry about the graph if you explain it to yourself, or the best, as I keep saying, if you can explain it to any of your peer group, any of your classmates, this becomes very, very easy, right? So draw the shapes, teach the topic. Bring a smile on somebody's face by liking, subscribing and sharing the video. Happy studying to all of you.